so in this section, I'm going to explain how solar panels work to used to convert um, light into energy into power. So solar cells are going to be known as photovoltaic cells, PV cells, photo meaning light, like from the sun, and voltaic meaning electricity. So as this name suggests, the solar cells convert this sunlight right here directly into energy that's going to power things like light bulbs and appliances and such. So typically these panels right here, as you can see, this is a solar panel, and panels are groups of cells grouped into larger arrays. So these PV cells are made of special semiconductors, and silicon is actually the most, silicon right here is the most commonly used semiconductor. So when light is going to strike one of these cells, the PV cells on the solar panel, a photon of light is absorbed. So you can see these are like photons from sunlight. Um, and so the energy of the absorbed light is going to free electrons, so electron flow, and energy is going to be transferred to this semiconductor, the silicon. So basically, PV cells are also made of electric fields that are going to force these free electrons to flow in a certain direction, which is the current of the electricity. So yes, that you see this current um, powering the light. So before I talk more about that, I want to just explain the importance of silicon. So silicon actually is going to have 14 electrons. And the first two shells are completely full of electrons, but the outer shell is only half full with 4 electrons. So the silicon always wants to fill its shell. However, pure crystalline silicon is not a good conductor of electricity because its electrons aren't free to move about. So the silicon used in these solar panels is going to actually be impure mixed with other atoms, and a lot of times the silicon is going to be mixed with phosphorus, which is going to have 5 electrons in its outer shell, and that 5th electron is going to be the important one. So phosphorus is going to be added to one of these panels, which I'll talk about what's going to be this N-type silicon, so that the electrons can be free. So typically there's the 2 layers. The first, yes, the N-type for negative, because of the prevalence of these free electrons. And the second layer is going to have added boron, which is this p-type silicon. And boron only has 3 electrons. So this p-type is going to have free openings and is going to carry this opposite positive charge. So we have a negative type silicon and a positive type silicon. So when energy is added as this photon of light from the sun, a few electrons are going to break free of those bonds and leave their atoms, leaving what we're going to call like a hole, basically. And the electrons that are roaming are going to try to find another hole to fit into, which these electrons that are leaving, trying to find this other hole, are going to be carrying this electric current, which is going to create the power. Now, since we have the 2 types, we have the negative type silicon and the positive type silicon, we've created this electric field. So the electrons free from the negative side are going to flow from all the openings on, from the negative side, we're going to rush to fill all the openings on the positive side. And this electric field is going to be a diode. So basically electrons are only going to flow from the positive side to the negative side, but not the other way. So each photon of light is typically going to free 1 electron, and the electrons flowing are going to produce this electric current, this electron flow right here. The electric current and then the cell's electric field causes a voltage, and with both current and voltage, we are going to then create power.
It's the week before final exams at LMU, and LA is experiencing quite a heat wave. A student whose room is sweltering decides she wants to find a way to air condition her dorm room without causing a loss of power to the rest of the building. She recently found a door to the roof of her dorm that is left unlocked, and she has the idea that she could install solar panels on the roof in order to power a window air conditioning unit in her room. If she directly hooks this up, then she won't need to use any of the electricity coming from the dorm. She lives in Hannon Apartments and her room faces directly south. This makes it an ideal location for solar panels to be placed, as it receives maximum exposure to the sun. She finds the perfect spot at the corner of the roof. With this, it will be a great place for her to place panels. A typical medium-sized window AC unit requires 1,000 watts to run, or 1 kilowatt. For her purposes, she assumes she needs a constant supply of 1 kilowatt hour. A typical solar panel has the dimensions of 164 centimeters by 99 centimeters. This means that the total area of one solar panel can be calculated to be 1.62 meters squared. It is also important to note that a typical solar panel has a maximum efficiency of 20%. In other words, a typical solar panel can only convert 20% of the solar irradiation received into usable energy. Based on national weather records in Los Angeles, the average historical daily solar irradiance in LA in a south-facing panel at a 45-degree tilt is 6.1 kilowatts per meter squared per day. However, we need the number to be per hour rather than per day. Therefore, we can divide 6.1 kilowatts per meter squared per day by 8 hours per day to find 0.7625 kilowatts per meter squared per hour. Then we need to figure out how many meters squared, or the total area required to produce 1 kilowatt, as that's the amount needed to power a window AC unit. If panels are only 20% efficient, the energy output will be reduced by 80%. Therefore, we calculate that into the amount of energy provided by the sun in order to figure out the amount of energy that will be put out by the solar panel. That number is calculated to be 0.1525 kilowatts per meter squared per hour. If we have 0.1525 kilowatt hours per meter squared and we need 1 kilowatt hour, that means that we need 6.56 meters squared. In other words, the total area of the PV panels needed will be 6.56 meters squared. So 6.56 meters squared divided by 1.62 meters squared for each panel means that we need a total of 4 panels in order to power one window air conditioning unit.